In the late 2000s, the term Terafab referred to a niche platform engineered by KLA-Tencor. It was a metrology tool designed to find microscopic defects on semiconductor masks before they could ruin a production run. But the word tera carries a specific mathematical weight, 1 trillion. This curve shows we have moved past mega and gigascale infrastructure. By 2026, a massive gap appeared on this chart. The AI boom created a sudden vacuum for electricity and computing power. Satisfying that vacuum requires physical hardware. We need millions of new servers, specialized liquid cooling systems, and massive solar farms capable of powering entire regions. This shift means that power generation and computing deployment must now occur at the terawatt scale. We have reached a point where human civilization requires more infrastructure than we have the logistical capacity to build using current methods. The core roadblock in solar energy is the construction process itself. It still relies on thousands of laborers manually lifting and mounting heavy glass panels in some of the most punishing climates on Earth. In computing, the problem is a fragmented supply chain. Building a single chip requires shipping components across multiple oceans and borders. These choke points cannot handle the increased volume. We cannot solve this by simply adding more cargo ships to strained transit lanes. In 2026, a new solution emerged in both sectors, a total reconstruction of the manufacturing process known as the Terafab. Two unrelated industries are betting billions of dollars that the only way to survive the AI boom is to change how we think about the factory itself. Terabase Energy is solving the solar bottleneck by moving the factory out of the city and directly into the field. Instead of building arrays by hand, they erect a climate-controlled Terafab tent on site. The entire facility is operational in 4 hours. Inside that tent, the assembly process is entirely automated. Robotic autonomous arms pre-assemble panels onto torque tubes, while inline sensors check for defects in real time. Once a unit is finished, a fleet of autonomous rovers carries the completed arrays out into the desert for final installation. This chart shows the speed advantage. At the White Wing Ranch project in Arizona, the Terafab achieved a 2-minute cycle time. A single field factory can now install 1 gigawatt of solar power every year. Because the system uses real-time decision-making to handle unpredictable desert conditions, it functions as physical artificial intelligence, managing the construction of the plant from the ground up. In March 2026, Elon Musk announced a different type of Terafab in Austin, Texas. It's a joint venture between Tesla, SpaceX, and xAI. Their plan is to collapse the entire global chip supply chain into a single building. This clean room is designed to handle every stage of semiconductor production under one roof. The facility integrates chip design, lithography using the Intel 14A process, advanced packaging, and testing. It removes the need for international shipping between manufacturing steps. The output consists of 2 chip families, the AI5 for Tesla's cars and robots, and the D3 processor, which is radiation-hardened for operation in space. The Texas complex targets 1 terawatt of AI computing output annually. This compute power supports a network of orbiting data centers powered by solar energy. By internalizing every step, the Musk consortium is creating a vertically integrated fortress, protected from the vulnerabilities of the global supply chain. Both the Terabase and Musk projects share the same DNA. They refuse to accept the traditional limits of logistics and labor. They both use physical automation to close the gap between a digital design and its physical deployment. But the risks are massive. Terabase is betting that their robotic rovers and field factories can survive years of exposure to extreme weather and desert grit. Musk's gamble is even more expensive. He is attempting to master sub-nanometer semiconductor manufacturing, a process where a single speck of dust can destroy a wafer, without any prior experience in chip fabrication. If these systems fail, the physical bottlenecks on renewable energy and AI expansion will remain, effectively stalling both industries. However, if they succeed, they provide a blueprint for a global network of autonomous energy and compute that can be deployed as fast as the machines can build it.